Cool. Last 2 weeks of the semester. So this week we will keep talking about cache side channel attack, Spectre, Meltdown. Then after that, I will talk about what is beyond this class for those who are interested in doing research in system and software security. What are the directions you should look into? Right now, we don't have a course at UB to cover those topics, but I used to have one, but I feel I should have more people in basic security before I have that class again. So I'm not offering that class right now. But if you are really interested in those topics, you can also talk to me. We can work together on research. So those topics are highly related to what we do on research. So next class would be quite simple, actually. So next class, we are going to watch a video together. It's a keynote speech given by a professor in CCS 2 or 3 years ago, maybe 2 years ago. So that keynote speech basically covers what we studied this whole semester. But you can say he presents those from a different perspective, but you are going to say all the problems we touched here. Okay, so before we start, one announcement is there is the final course evaluation. The same rule here. If 90% of the students submit an evaluation, all of the class will get some bonus points. So we have 42 students at this moment. It means I'm looking for 38 evaluations to give out the bonus. Okay, so today we'll keep talking about Meltdown and Spectre. And before that, we have we finally have those 2 experiments set up on our server. One is a cache. Another one is a cache attack. So you can say, so actually they work for 32-bit and 64-bit, but the TA only put the 64-bit here. So let's take a look. So you already looked at the code last week. So this is the source code of the program. It's only a main function, and there is a local variable, then 2 timers. Those timers are not local variables. We directly put them in registers. This is how you put a variable in register in C. You just use the register keyword. That's a C keyword. So this keyword tells the compiler. The programmer want to put that in register. Then the compiler should try its best to put those in register instead of on stack. Then there is an address pointer. Also, we initialize array. So the array is big. One page is 4K, and every array here is actually 1 page. Then we initialize 10 arrays, which is 10 pages. So after that, we use the save flash. This is a save flash function here, but eventually it's a CL flash cache clean flash instruction at the Intel architecture. And this instruction, you can execute it at non-privileged level, just user space. You can execute that instruction. Some architectures, those instructions, you cannot really access them at the user space. You have to do them in a kernel, but in Intel, you can do that user space. Then we access 2 items there. One is index 3, another one is index 7, right? So when we do this access, we're actually doing writing here. But when we do this writing, the first thing is the CPU will bring that byte, or actually that cache line, into the cache. Then write that, then optionally write back to the memory. So by doing that, these 2 statements will bring the cache, the memory, and those 2 cache lines into the cache, 3 and 7. So after that, technically, when we access all of those 10 items again, we should be able to access the item 3 and item 7 quickly than the other items, because those two are already in the cache. So if we run this program, by the way, we put the makefile for you here. The makefile is also under code. So you can compile this program by yourself. After you compile it, it will go to the temp folder. We also have a compiled version at the root folder as well. This is a compiled version. If we run this program, you can say we measure how long does it take for the CPU to access a specific item here. So for item 0, it takes like almost like 500 CPU cycles. So tier 2 also, 1, 2 also almost 500 cycles. But the 3, you see, it's just half, 240 CPU cycles. After that, we go back to 500 cycles. Then 7, 238 CPU cycles. 8, for some reason, is high. 9, 500 cycles. If you run this multiple times, you can say, this one, the first one is very slow, but all others are quite consistent, around 500. Except 3 and 7, they are fast, right? So if we run that again, you can say, this is quite consistent, right? So when you do a real measurement, if you are doing attack using this, you probably want to measure this many, many times, 1,000 times, and get the average. Okay, but we run it four times so far, you can say the result is quite consistent. It's in the cache, it's like a half of the time you will use if the code is if the data is in the memory. So if we can, let's go to the code and we just change the code here. So let's say we just try the 3 and the 7, right? Maybe we just change to 5 and 8. Let's say, then we make some game. Then the code will be in temp folder bin cache time 64-bit. You can say now we changed to 5 and 8. Right? Still, quite consistent. So the index 5, around 250. 8, around 250. All others will be higher than 400, around 500, right? So, but especially at the boundary, sometimes it's getting weird. For example, this one, now it's very, very fast. But previously, the first one was very slow, okay? Some of them, we don't know what's going on. But you can say those are still consistent. Okay, so this shows that cache side channel attack is reliable to some extent. There are a lot of things we don't understand because technically only those cheap manufacturers, hardware manufacturers, they know exactly how things work. We are observing a gray box here, not a black box. We have their document. The document explains what's going on, but not everything. That's why we do a lot of tests to try to understand what's going on. So that is the cache time experiment. The other one is the flash reload attack. So for flash reload attack, we also have the code available. So the flash reload attack can be used for for one process to attack another process. But in this example, we are using one process to be the victim and also the attacker at the same time. So the main function here, we have first, we flush the side channel. Last class I said, flush basically means evict some cache lines from the cache. Then we run the victim function here. So So after we run the victim function, so the main function basically is the attacker here. The attacker will first flash the cache, then run the victim function, then after that do the attack. The attack is the reload function. So the purpose is to measure what items in the memory the victim just accessed. So the array we have here is also big, 556 pages. One page is 4K. Then let's say the secret we have here is 94. Okay, that could be an ASCII number, right? 94. Then the flash is called by the attacker. What the attacker does is to first bring what in the RAM. Well, this is actually to prevent copy on write. That's a technique Linux use. So when Linux fork a program, the new program is almost the same as the old program, right? So if you really want to change the new program to another, you want to run another program, you have to make another system called execve. We say a lot that. So, but it's possible that you do not need to make the system called execve. Like if this is a web browser, a web server, you get a get a new web request, then you just want to fork yourself and handle the web request in a new process. So you do not, you only execute a fork. You don't really execute execve. So since you are not executing execve, or even if you are executing execve, you may use some of the libraries, some of the memory regions with the previous program. So from the operating system's point of view, it's better that we do not make another copy of those shared regions to just save time, because make a copy of those where we need to spend a lot of time on that, right? But sometimes a new program will write its own data to those regions. In those cases, you have to make a new copy. So the old program and new program, they have a different copy of the physical memory in that case. So that is a technique called copy on write. So only if the new program write on a memory region shared with the old program, the OS will make another copy of it. So they have a different copy. Otherwise, physically they have the same copy. Okay. So that can significantly make your system run faster. So the purpose of this line is to prevent the copy on write. So we want to we want to make sure this process is not sharing those memory regions with the old program, because the old program here is the shell. The shell will fork a new program called a flash reload, right? So that's the purpose. After that, we just flash all of them from the cache, all 256. 256 cache lines will be 64 bytes. Each cache line is 64 bytes. They will be brought into the cache. Then we flush them out, and we make sure. So after this step, we make sure none of them is in the cache. After that, we run the victim. The victim is just accessing one of those 256 cache lines. This is how the victim accesses it. It will just do a variable read here. It's an array. The secret is the index, and you bring that into a global variable. That's it. After that, we're going to measure all 256 cache lines to measure how long does it take for the attacker to access it. So the idea is the victim just accessed. In this case, we're only accessing one. The idea is that one, the access time should be much shorter, much faster. So if we run this program, so let's say here we actually set a threshold here. We may need to adjust this threshold. So the threshold here we set is 240. If it's under 240, we print it. If it's higher than 240, we do not print that. So if we run this program, you can see that it's quite consistent. Every time we run it, we will figure out of those 256 items, the victim accessed 94. Okay, well, this is very, very consistent on the server today. So if we change the program a little bit, okay, give me a number between 0 to 255. Which one you want to try? We just change it. Just give me a number. Throw me a number. 1? Okay, 1 is a tricky one, because it's at the boundary. Yeah, but let's see. So it may not be that reliable. Oh, we don't have a... Oh, did the TA put it? Oh, sorry. I should go to the code folder. Let me go. Then let's go to temp bin flush 64. Well, it is quite reliable. Yes. Yeah. So you can say, in this case, the attacker will be able to steal or to figure out what memory locations the victim has been accessing. Also, this can be used as a covert channel between two communication parties. You can use cache to send out a message from one process to another process, and also from a user land, from a kernel to a user space program. So that's what the Meltdown does. So let's go back to the Meltdown example. So let me remind you again, what is Meltdown? So Meltdown allows attackers to read arbitrary physical memory of the kernel from an unprivileged user space. This problem exists because of the out-of-order instruction feature of the modern CPUs. Fortunately, or I should say unfortunately for our class, this has been patched for most of the CPUs we are using today. So if you check the CPU, the server, you can say Meltdown, just do a ls CPU, which you did in your homework last week. You will say, where's Meltdown? So Meltdown is not affected anymore. Okay. So this was discovered like 4 or 5 years ago and has been patched very soon at the CPU level and also at the OS level. Before they patch the CPU level, the OS level, they have some solutions. But Spectral is harder to fix. That's why you can say Spectral, the CPU doesn't say not affected. It says, kind of say, hey, we're trying to mitigate this using those approaches, but there's no guarantee, or some of the approaches are software-based, but there's no guarantee this attack doesn't work anymore. Okay. So go back to Meltdown. So still, we can take a look with this animation I made, how Meltdown work. So first, we have a user process. Since it's a user process, everyone can compile a program or write a program and execute on a computer. It could be a cloud computer. Maybe it's a cloud computer with multiple containers, and each container, like our environment, right? We only have one big virtual machine for all of you. Whenever you log in, you have your own container, but you are sharing that virtual machine and also sharing the physical machine underlying. So every time you run a program there, you create a user process. And that user process is trying to steal some information from the kernel. Here, the assumption is we know the physical address of that secret in the kernel. So what happens is the user process tries to read a byte or more bytes from arbitrary kernel address, and obviously this should be stopped, right? So modern CPU has privilege separation for almost 40 years, maybe 40 years. Well, so early 2000, no, not 2000, like Windows 95 do not really separate applications and kernel very well. That's why Windows 95 had a lot of blue screen of death that time, because the user program can sabotage the kernel all the time. Sometimes just the user program, the developer made a mistake, not necessarily a malicious intent there, but still it can damage the kernel, so the system crash. Then Windows 8 or Windows NT changed that picture greatly, but still that's like 25 years ago or 20. But the hardware feature for privilege separation has been there for, I believe, maybe 40 years. So after this privilege separation, we just believe the user space cannot read kernel's data or cannot write kernel's data. And this vulnerability showed us actually we can do that. So the vulnerability has been there for 40 years. No one discovered. So the user program tries to read some kernel space address, and obviously the CPU should generate an exception. The CPU should not allow the user program to do that. However, because of out-of-order execution, basically the CPU has two things to do when the user space tries to access that. The first, the CPU needs to decide whether this access is legit, whether this program's access to that memory is allowed. Okay, that the CPU has to look up at the MMU, the page tables, because the permissions is a page table. The page table shows this is a kernel memory, this is a user space memory. And as long as it's related to page tables, it could be slow, okay? Then the second thing is, after the CPU decide, the program has the permission to read that, the CPU has to bring the content at that memory location to the register of the user program. So those are two different steps. Technically, you should do the first step, then the second step. But by doing that, it will be very slow. That's why we have the out-of-order execution. So what the CPU actually does is, it will first bring that into a register, and at the same time check whether the program has a permission. And that check whether the program has a permission takes longer time than bring to the content to the register. So after the content is bring to the register, then after a bit longer, the CPU figured out, this data, the program has the permission to access the data, then just keep going, no problem. If the CPU find out the program doesn't have the permission to access the data, then it will just revert the register, okay? So no error happens. However, there is a design error or design flaw. Because when you bring the content from memory to the register, you actually first bring it into the cache. So after you bring it to the cache, and the CPU figured out the program should not have the access, it reverts the register, but it doesn't flush the cache. That is where the problem is. Since it doesn't flush the cache, the content which the user program should not have access to stays in the cache. The user program do not have an instruction to directly access what is in the cache. But it can develop some clever methods to infer what has been brought into the cache. And that is how what Meltdown works. Okay? So for example, in this case, we want to access some secret data. And in a second step, the secret data is brought into the cache. Then after that, an exception is triggered that discards the out-of-order execution results. So the secrets will not be brought into the register. However, the secret stays in the cache. Then after that, the user program can do some clever side channel attack, like what we just saw there. It can come up with something like this. We brought an array there, then we just try to read that array, and each time we read 1 byte, just like the example I showed you before. Every time we write 1 byte and use that 1 byte as an index of another big cache data, then we measure the time, how long does it take for us to read that data. Then we can infer the secret here. So this is the source code of the kernel part. I think we briefly talked about this, but let's go over this again. So this is a vulnerable kernel. The kernel has a secret, and the attacker's goal is to steal that secret. The secret is 8 bytes, so every byte is just a ASCII here, but technically it can be anything from 0 to 255. Then this kernel module has an init function to initialize this kernel. It shows the kernel data's address. It creates a kernel heap to move that kernel data just to access that kernel data. Then it exposes an interface in the Linux proc file system for the user program to access. It has an open interface, also a read interface. But the open interface and read interface, they are not going to disclose the secret. The read interface will only read the buffer from the kernel local variable to the kernel heap. It's not going to give that back to the user program. The user program wants to steal that. So this is a simplified version of the user program try to steal that kernel data. Only 4 lines. This is the address of that secret. This is a physical address. We get the address, then we access that address. Okay? Here we just want to steal 1 byte each time. That's it. And what should happen? This should be a segment fault, right? So our old friend segment fault here, because you are trying to access a kernel data. So when you do that, this 9, so before last class, we only know that this 9 statement will trigger a segment fault. We do not dig into the details here. Technically, 2 steps. One is the kernel will check if this one is legal. If it's not legal, it will trigger segment fault. If it is legal, it should bring the data to this local variable. But actually, like I said, they may bring the data to the local variable first, then trigger, after that they find out this is not legal, they trigger the segment fault, and also clear this local variable there. So if our code is as simple as this, the data will be brought into the cache, but we never have a chance to read the data out, okay? We don't really have a chance. That's why our code will be modified like this. First of all, we are going to handle the segment fault signal. That's a Linux signal. So when segment fault happens, the default handler of our program will just abort our program. But our program doesn't want to abort. So we will tell the Linux kernel, I'm going to handle segment fault by myself. So when a segment fault happens, instead of just exit, I will call the function called catch segment fault. And the catch segment fault function is just use the signal long jump and signal jump. So C programmers, probably you use the set jump, long jump, which is provided by the C interface. But at the Linux level, Linux also provide the signal set jump and long jump, which is very similar to the long jump set jump in the C library. So here in the main function, we first have the location of that the secret. Then we tell the Linux kernel we are going to handle the segment fault. Then we have a set jump here. So when set jump returns 0, means this is we are setting it. If it doesn't return 0, we will go to the non-jump actually. So here you can see what we do is we just access the data. Then we print out the data. Otherwise, they will print out the memory access violation. So if it's not successful, we will just keep trying in this case. When this part is not successful, what will happen? It will raise a segment fault. And because it raises a segment fault, we actually go to catch segment fault, then we call long jump, then we return to here again. We try that again. So this is not guaranteed to work every time. That's why we keep trying. Okay. After we keep trying, then it can give us the secret. Then this is the bigger Meltdown function here. You can say what we are going to do here is the kernel data is this. So what happens here is this one we're trying to, this one still is not going to work, but because the CPU will not put that into the local variable, the CPU will only put that into the cache. That's why we try to extract that information from the cache. So the first thing is we flash the side channel. So this goes back to the flash reload. We flash the side channel, then flash 256 pages. Then we try to call this Meltdown function. Oh, it's here. We try to call the Meltdown function to access that. And here the access here is very smart. You can say, first, we access this into a global variable. But if the segment fault is generated, we're not going to get the data in the local variable, okay? So what we do is we quickly use that local variable to bring something else into the cache. We use that global variable as an index of that big list of pages we created there. We bring the index there, in all of those pages, into the cache. We don't care about the content we bring into the cache. We care about the location we brought into the cache. And that location, that index, is the secret here. Okay? So we are hoping those two statements will execute before the kernel figures out, oh, you don't really have permission to do that. So after those two statements executes, that cache line has been updated. Okay? We don't care what has been the content to be updated, but we know which cache line has been updated. That which is the secret we're trying to get. Then the CPU find out, oh, you don't have permission, then it will clear kernel data, but it doesn't matter anymore because we're not going to read from kernel data. Then after that, we just do a renode attack. So you can say this piece of code is the same piece of code we used before in the flash reload, right? So after that, we figure out, this kernel data has been brought into the cache. So you are going to do this in your homework, but unless you are using an old CPU, it's not going to work. So what you can do is, if you do not have an old computer, just follow those steps, try to understand the best as you can. Even if it doesn't work, have some screenshot, show it doesn't work. But if you do have an old CPU, you can try those. Just need to be 5 years old. Okay, it should work on 5 years old CPUs. Yeah. So that is Meltdown. Then moving forward to Spectre, which is harder to mitigate than Meltdown. They are quite similar, so it also relies on the out-of-order execution, but also it relies on something called branch prediction, like I explained last class. So in branch prediction, it's very similar to the out-of-order execution here. So let's say we have a very simple C code. We're using C code to show this, but you can understand everything here is machine code. So we have a data, which is 0. Then we have a variable x. We compare x with a predefined size. If x is smaller than that, we add 5 to the data. Otherwise, we do not do anything. Okay. So you can imagine this. The CPU cannot execute 2 branches or multiple branches at the same time, even in out-of-order execution. So the CPU right now the CPUs will just choose 1 branch to keep executing. So the CPU will guess which branch is more likely to happen in the future. Then I will execute that branch, and that is called speculative execution, and that involves the branch prediction there. So how does the CPU do the branch prediction? How does the CPU guess if the x is smaller than size or bigger than the size? So those super smart hackers, they find out the CPU actually learn from the previous executions. If you execute this piece of code many times, 20 times, 10 times, the CPU will actually remember, oh, every time or most of the cases, x is smaller than size. Then when CPU do the branch prediction, it will predict x is smaller. Then it will keep executing what is inside here. And you can imagine what we do here. What we're going to do here is something illegal, right? We will just net the CPU to execute something illegal before the CPU realizes it should not do that. So the first version of a Spectre is use those conditional branches, those if instructions in if statement in C. We already see a lot of those instructions at the binary level. That's basically different jumps, right? There will be a compare, then after compare, there will be a conditional jump. Then the CPU will be trained to believe one branch should be executed. The second version of a Spectre is indirect branches, like the call EAX, call jump EAX. We saw those things on the Rob gadgets before, and also on we probably did one buffer overflow on that as well, right? So those ones, the CPU will also make predictions on the register value and keep executing there. So here is one example. So we have the main function. We are still going to use the flash and the reload approach, and also we are using one process to demonstrate this. So real-world attacks, you should have multiple processes, right? The victim has a process, the attacker has a process. Doesn't make sense if the attacker is already in the victim's process address space. Those processes, they should run on the same physical machine. Doesn't necessarily have to run on the same physical virtual machine. Okay, it could be we're talking about one cloud server in Amazon cloud. Then you have a virtual machine. Attacker has another virtual machine. Your virtual machine runs some encryption, and the other virtual machine has attacker's code to try to steal what you are accessing here, because they are sharing the same CPU. Okay. So the first step we do is we flash the cache, get the cache ready. Then we train the CPU. So this is the smart part. People figured out, oh, it works. We can train the CPU to believe what path will be executed. So we have a for loop here. We execute it 10 times. In all those 10 times, we execute that victim function with number 0 to 9. Okay? So the size here is set as 10. So every time we execute this, it will be, this branch will be taken. Okay? So we are going to bring something into the cache here. And every time we're going to take this branch. So CPU is trained this way. Then after that, we flash the size variable, also flash the cache. Then we run the victim program again, but this time we're giving it a big number, 97 here. Previously, we're giving it a small number. So because we flashed the size here, now when we run the victim program, this predicate, this statement, will take longer because the CPU has to read that from the memory, right? And also compare that. And because of that, the CPU will, based on its own guess, will start executing this line of code. And this line of code is accessing actually 97, okay? Not something smaller than 0 anymore. So technically, this should not be allowed, okay? You should not read that data into the temp, okay? However, the CPU will do that. We would not directly get that from the temp local variable, global variable here, but we are going to bring that into the cache, and then we do a reload attack to probe which cache line has been changed. Then we can infer. What that secret is in that particular address. So that is how Spectre works. So So this week, you are only going to do the homework of Meltdown. Next week, you are going to do the homework of Spectre. You just follow the steps. So they will not be very hard, but not guaranteed to work on your CPU anymore. But you can imagine 5 years ago when those two came out together, it's a huge shock to the whole computer system community, not only the security community. So the cache side channel attack, the Spectral, at least the Meltdown and Spectral, they will not be in our final CTF because we cannot do them on our server anyway. So we're not going to have but still, you can try to do that in your homework. Okay, any questions so far?
So when you mentioned that the CPU remembers based on previous executions, where exactly is that data stored?
Well, that's obviously in the circuit level, the microarchitecture level of the CPU. I don't know how it works. It may have its own register or whatever. For example, the CPU remembers a lot of things, like the cache. The cache, we said there is a cache eviction policy, right? So the Intel CPUs, they use very complicated policies, like the least recently used policy. And since it's least recently used, you have to remember which ones are are used recently, right? So those are also need to be remembered. So
on the CPU processor?
Yes, yeah, it's part of the CPU. Yeah, all of those are part of the CPU, not software. Yeah, that's why for most of the software guys, we still treat this as a gray box. First of all, we are not electrical engineers. We're not that good understanding how things goes on there. Then also at the CPU level, some people use microscope to look at the circuit. Even yesterday, I saw on Twitter, someone used microscope to reverse engineer the x88, the very first Intel CPU, and he said, hey, he find there's a bug, and he find how the Intel engineers fix that bug. I can find that and share you guys on Slack later. Yeah, but now you can imagine at even the hardware layer, there has been a lot of. First of all, there is a risk of IP problems, right? If we can reverse engineer the CPU designs, maybe we can replicate those CPUs. So even the hardware layer, there has been many different protections, obfuscations, to kind of like software obfuscation. You look at the disassembly, it's very difficult to understand what's going on. The hardware, the same thing. The hardware layer, they have circuit level obfuscation to make it very difficult for you to understand what's going on there. Okay. Other questions?
There are some more computers in the library, maybe 4 years or so.
Yeah.
They work.
Yeah, you can. Yeah. Yeah, you guys can try those computers. At least, so what you are going to do in this homework is you are going to use a virtual machine to do this. But in that virtual machine, you compile this program as native. So the program are actually natively executed on the CPU. So make it portable, and also at the same time you can do the homework. But you need an old CPU, a little bit old CPU, and a little bit old system to do that, because there are also software layer mitigations to stop those attacks. Cool. Other questions? Okay. So that's basically all the important topics of this semester. So the next 1.5 course, you can relax a little bit. We are talking about things beyond this class. Or next class, there will be just a video from one of the top researchers from industry and also from academia. He's a professor at Georgia Tech and also at the same time a senior vice president at Samsung. So he's leading Samsung's all security projects and also a professor at Georgia Tech. So he gave a very good keynote to cover all we cover in this class. Yeah. So for the rest of this class, I want to talk a little bit about. I can see that many of you enjoy this class very much, and if you want to pursue a career in this direction, or you want to learn more around this direction, or let's say if you just want to work with me on this hacking stuff, then what are the paths? What's the roadmap? Okay, so this course, I call it software security, right? So you can say this course, we do a lot of, I would say there's baby steps of software hacking. Of course, some of you actually attend my hacking group meetings Friday. So there we do baby steps in hacking right now, but they're not necessarily binary hacking. A lot of those challenges are designed for you to learn how to use Linux, how to hack a website. Those are also baby steps, but still, you can say there's a huge gap between those kind of hacking to binary hacking. But this class is still the basic baby step for binary hacking. So you learned many different types of binary bugs, binary vulnerabilities. Not all of them. There are something else we didn't cover in this class. For example, integer overflow. I haven't developed a module for that yet. Also, risk condition. I haven't developed a module for that yet. So real-world bugs, real-world exploits usually combines a lot of techniques you learn in this class together. So here we're trying to separate it clearly. When you do a buffer overflow, you do a buffer overflow. When you do a ROP, you do a ROP. Sometimes you need to, in real world, you need to combine a risk condition with a use after free or double free. Combine those together. In this class, you learn how to exploit those bugs, and I show you the source code. So in real world, most cases, you do not have the source code. Okay, you only have the binary code, and you need to exploit that. I would say, I try to make this class self-contained. So some of you, even if you didn't take OS, system programming, or compiler, I hope you still could enjoy this class so far. But if you really want to have a solid background, those other courses I highly recommend: OS, compiler, system programming. So after this class, I used to offer another class called Advanced Software Security. I only offered it once here. Then I realized it's too early for me to offer this class here because we do not have a big student body who knows software or binary hacking in the first place. So in that class, what we do is we learn how to develop tools to automatically discover and also exploit those vulnerabilities. So far, you're looking at the source code, you see the vulnerability. And the source code I gave you is very simple. So imagine there is a huge binary compiled from like several hundred K line of code. It were impossible for you to look at it and find, oh, there is a bug, right? And most of the tools are developed by professional developers. The bugs will not be so obvious, but still, it's full of bugs, for sure, right? So the research is how to automatically discover those vulnerabilities before the products are shipped, and also how to automatically exploit those vulnerabilities. You can imagine some agencies like DARPA, like NSA, they may be interested in how we can automatically exploit, weaponize those kind of things, right? And also advanced defense. So you can, even in this class, you can say the defense can be at different layers, and they should be at different layers. There are defenses directly at the CPU level. We change the CPU, we change the memory system. There are differences like address-based layout randomization at the OS layer. There are differences at the application layer, like stack cookies, which is basically a free, stack cookies like super fast. It's like a free solution, even though it's not very useful, but it's free. Other solutions could be very expensive, like Shadow stack, a little bit expensive. Other approaches. The academia propose a lot of good ideas. They can eradicate the problems, but they are not just practical, right? Then there could be new languages like Rust. So Rust at the compiler time makes sure the program is safe. However, as far as I understand, it's very difficult to program in Rust. Your program just cannot compile because there are safety issues. It cannot compile. But to fully understand, to fix those issues, takes a lot of time and expertise. That's why a lot of people right now, they are writing unsafe Rust. So Rust have a feature, you can just say, this part is unsafe. So compiler will not enforce those very strict rules. A lot of people are using Rust in an unsafe way. Then it's not really Rust, right? Okay. So in that class, we cover those topics. And today I'm trying to give you an overview what are included in those topics. And of course, if you really want to be a system or software researcher, then after that advanced software security class, I feel what you need to do is read more papers, writing more code, read more code to understand exactly how the system works. That's what we do in our lab every day. Right now I have 5 PhD students. 2 of them are actually sitting here. So their job every day is reading those code and also changing those code. We develop our own systems to secure different architectures, mainly ARM-based. Many Cortex-M, those IoT devices, but also we have projects on Cortex-A. I used to work on Cortex-A, so Cortex-A are for those kind of devices, phones, laptop, servers, x86, Intel ones for servers, desktop, then Cortex-M for very low-end microcontrollers. We also work on FPGA. Today I will cover those 4 topics, static analysis, but you can say all of them, they are automatic. They are not manual analysis anymore. The first one is static analysis. The second is fuzzing. Then dynamic taint analysis and symbolic execution. So obviously for any practical tools, you need to combine many techniques together. Let's start with the static analysis. Static analysis means you analyze a program without running the program, okay? So what is a tool always do? What is a tool always does static analysis? Compiler. Compiler always does static analysis on the source code, right? So in our research, we mainly use LLVM. So far in our class, you can say, this semester all our code were compiled using GCC. Yeah. But in our research, we usually use another tool, LLVM. That's a compiler developed by at UIUC maybe 20 years ago. So for what we do, usually we write LLVM parsers. So give me a source code. Imagine, give you a piece of C code. Then you want to add stack canaries there. So how do you add that? You do not change the C code. The developer doesn't change the C code, right? The canary is automatically inserted there. There are several instructions there, right? The instruction to read the canary, the instruction to put the canary onto the stack. Then at the epilogue, we compare if the canary has been modified, been tampered, right? So basically, you are adding instructions into the original C program. And that step is called instrumentation, okay? So LLVM is very convenient for you if you want to add some instructions into a program. You just need to develop LLVM parsers. And LLVM itself is developed in C++ using the standard template. So itself is very complicated. But if you only want to do what we do, it's not that complicated, okay? It's not like we are trying to optimize the code. We're just trying to instrument the code and also analyze the code a little bit, right? So LLVM is open source. It's a compiler infrastructure. It can compile different source code to different machine code, and let me see if I have the figure for that. Oh, I have a figure later. Yeah, let's go there later. Okay. So it has its own intermediate language called LLVM IR. So no matter you write C code, you write C++ code, Java code, or Rust code, it can first be compiled into one single unified language. It's called LLVM IR. Then the LLVM IR will be compiled into different machine code or different, not necessarily machine code, other code. So this tool was released in early 2000 by so this Chris Nettler. He is in industry right now, obviously one of the best developers in the world. There are several people in the world developed crazy software that everyone uses, right? Like Linus developer Linux, right? Everyone uses that. I mean, if one day you get an email that he yell at you for your bad push to the Linux kernel, I mean, forward that email to me. It's always exciting to say he yell at people, you know. Yeah, even that you feel you are honored, right? You will be yelled at by Linus. Then there's another guy developed the QEMU emulator. That's a crazy project done by one person. Then also this guy Chris Nettler, he basically developed LLVM when he was a student at UIUC. I don't remember he was a PhD or master student there. His professor is still at UIUC. So it had almost been 20 years. I believe he's not really involved with this project anymore, but LLVM has been very mature since then, more and more mature since then. There is a big open source community behind it. People are keep contributing to this project. Itself, like I said, is developed in C++ using STL. So if you have experience writing C++, you know it's actually a very challenging job. STL is not easy to use. It's very, I still remember I used to write everything in C++ and STL, and it's just very painful sometimes. If you have a memory corruption bug, and you can write a program in one day, but spend 2 weeks just trying to find out where the bug is. Sometimes it's really painful. I'm not writing as much code as I used to write. I should write more, but I'm not writing a lot right now. That's a downside of being a professor sometimes. Yeah. So this is, if you are interested in this, take a look at their webpage. It's actually split into multiple sub-projects. So the architecture of LLVM is like there is a front end to translate whatever language to the LLVM IR. Then the optimization is done at the LLVM IR level, which means it doesn't matter what the source code language it is in. You can use the same optimization algorithm, okay? Some other compilers cannot do that. I mean, some compilers specifically for one language, and the optimization is can only use for that. So the beauty of LLVM is compile everything into its own defined intermediate language. Then after that, we get the back end. Then the back end can generate the back end can generate the machine code. So what we usually do is we develop modules that will be called by the optimizer or back end. So they are called LLVM passes or LLVM backend passes, I believe. Yeah. So we do not really fully understand the whole LLVM. So this is a picture I showed you in the very first class this semester. This is usually how GCC works, right? So you get a C program, you change to .I program, then assembly. Okay, GCC will change that to assembly. Okay, then the assembly will change the program to the binary code. So you can see that this part, GCC is like a big program to do all the things in a program, in one program. But LLVM try to split this into, modularize this into different components, different steps, like this. So the front end is actually called CLAN. The CLAN will change all kinds of languages to its own LLVM bytecode or the IR. It can be either .bc or .ir. They're basically the same thing. The .ir is a human readable, .bc is bytecode. You cannot read that. Then optimization, all the optimization is done here. Then after that, it will still be IR or BC, but it has another back end to compile that into a different machine code. It's called the LLC, then there is LLD as well. So the back end, you can compare it to anything. You can compare it to ARM, Intel, or you can even compare it into WebAssembly. Okay. So WebAssembly is something new. Came out, I don't remember when, maybe 5-6 years ago. It's widely used now in our browsers. So we can skip this one, CLAN or class++. I want to talk a little bit about the LLVM instruction set. That's their own intermediate language. So its own intermediate language, so they translate every language into this, right? So their intermediate language is kind of like a RISC instructions. It has 3 addresses, the source, 2 sources, 1 destination. And it's human readable. It's strongly typed. It has explicit control flow. Some of the instructions, machine instructions, okay, Intel, ARM, they do not have an explicit control flow. When you read out that instruction, you don't really know where this instruction goes. But for convenient program analysis, they have explicit control flow. Then there are many virtual registers, and the virtual registers, the syntax is started with a percentage sign. And all the instructions, they are in a static single assignment form. I will explain later what this means. If some of you work on programming language, you should be familiar with this. It also abstracts away those machine details like calling conventions or stack references. So when you read out those instructions, they are exactly something between the C code and the binary code, the machine code, the Intel code. Okay. It doesn't look like C code, but at the same time, it doesn't look like the machine code. Some of the information is abstracted away. Let's say, so what is a static single assignment form? So this is a form defined or principle we use in compiler design. This is a property that intermediate, so it requires that each variable will only be assigned exactly once. That's it. Every variable will only be assigned once. When you write in high-level language, you don't do that. That's why you have a variable, right? You have a variable, you assign a value to it, later you change that value. So, but because of that, it's very difficult to do analysis. And back in 1988, those researchers published a paper in the Best Programming Language Conference, POPL. It's called a Principle of Programming Language. So they argue that we should have a a language that have this static single assignment form. It will make much easier for us to analyze the program. For example, usually when we write a program, we write it like this. There is a variable y, we assign it to 1. Later, we assign it to another value 2. And x will be assigned a y. So if we translate the program into an equivalent program, but in the SSA format, then we have to create new variables. Okay. So y1 has a value 1. y2 has a value 2. So in this case, those two y's, you can see, they're not related anymore. When we look at this piece of program, the feeling is those two statements, they are related, right? But when we translate to this, we figure out, oh, actually they're not related. So make our program analysis much easier. Okay. Then x1, so when we look at it here, it's not clear x has a value of 1 or 2. If you trace back here to say, so you need to do complicated program analysis. But in a single format, SSA form, it's very clear. So it will make your program analysis algorithm much simpler to develop. So if you want to develop a LLVM pass, usually what we do is just develop those kind of passes. You can develop a module pass. You can think this is some code will be applied to a single source code file. Then there will be a core graph pass. It will traverse a program bottom up. There could also be a function pass. It will run individual function. So imagine that stack cookie I told you before. So if you want to implement stack cookie, then you will implement a function pass, right? Because you want to modify each function code. Right? Then there is basic block pass. So some of you in this class, you use the tools like Battery Ninja. So Battery Ninja will give you some kind of like a core graph there, not necessarily core graph, like a control flow graph inside a program, right? And that control flow graph, there are a lot of blocks. And that each block is called a basic block. So in each basic block, the control flow is just a sequential. But get out of the block, it may not be sequential. It will jump to different places, right? There are other passes. Also, those passes, you can say, you develop those passes because you want to change the code. If your pass doesn't change the code, you can just develop analysis pass. Those pass you change the code is called the transform pass. Okay. So that is about LLVM. So LLVM is kind of like the. So excuse me, guys. What are you guys talking about? Okay. So I don't want you to influence other people. Okay. Okay. So obviously LLVM is one of the most important tools we use, but also we have other tools, other techniques to find bugs. So how do we find bugs? The first thing is use your eyes. Yourself, treat yourself like a machine and try to say if there are bugs. And this is still approach used in industry, right? There is a peer review process to review code. The problem of this is obviously, first of all, it's not scalable. It's not easy to identify bugs. And also, it takes a lot of expertise to do that. Then we have static analysis, which we do not run the code. We also have dynamic analysis, which we do run the code and find bugs. And one of the very practical, useful approach is called fuzzing. So fuzzing, the idea is just so simple. You just give garbage input to a program and say how it behaves. If it crashes, it means there's a bug. Okay? Maybe there are other indicators, not necessarily just a crash. Okay? But if it crashes, then obviously there is a bug. So fuzzing basically executes a program many, many times. Because it executes a program, it's a dynamic analysis approach, and it will give it all kinds of input. This is very effective when applied to standalone applications. Fuzzing doesn't really generate false alarms. If the program crashes, then there must be a bug. It cannot be a false alarm. Right? But static analysis sometimes can generate false alarms. So in bug discovery, we have we discover known bugs and also unknown bugs. It sounds a little bit weird. Why do we want to discover known bugs or known vulnerabilities? Because it's very. How many of you, when you do homework, you copy code from Stack Overflow, GitHub, and other places? No one? Well, everyone does, right? Everyone does. And now we even have the GitHub Copilot, right? You just type some comments, and it will generate code for you. How do you know those code you can trust? How do you know they do not have bugs, right? So some of the code, like Copilot, it will just generate code based on its learning from other open source projects. And other open source project, we may already discover there's a bug. Now it's in your code. Can you find the same bug? That's one thing. Another thing is, how do we discover unknown bugs? No one knows that's a bug. Those are usually called the zero-day vulnerabilities, right? So that's why we have all kinds of approaches. We combine them. So fuzzing is very useful. You can use that to fuzz any program. Okay, there's no matter what kind of input it takes. It could be a web server. It could be a picture viewer. You just generate different input, feed it to the program. You hash that. Right? So let's say how fuzzing works if that's a standalone program. First, we have a standalone program that's an executable file in our file system. Then we create a process for that executable file. And that executable file has to take some input. All the program, I would say all the programs we have right now, they take some input, right? Either from the user, either from network, or from some sensors. They take some input. Then the fuzzer has at least two modules. One module is the input generation module. It will generate random input. And when I say random input, it doesn't necessarily to be uniformly distributed random, right? So this is where a lot of research goes on. How do we generate random but input that are more likely to trigger a bug, to trigger an exception, right? After that, we also need another algorithm. This algorithm should be able to observe the process, and it should tell if the process is behaving correctly or not, right? One of the indicators is crash, but sometimes not necessarily. First of all, if it's a crash, it means it will be very expensive, right? Because it's a whole process. A process is created, a process is terminated. From OS point of view, that's very slow. It takes a long time. So because of that, there are other modules to make this program, to make this fuzzing process much faster. One is we do not directly create a process for that. We do not create a process for each input because that would be too slow. Can we just create a process, then keep feeding different input to the same process? So we save the time of creating process, right? So you can say those work are more like the system level, the OS level. How do we do this? And also, how do we smartly generate the test cases? The test cases are also called the corpus or test suite here. So how do we reserve the behavior, then cleverly design the next input that is more likely to trigger a bug? Three types of bug. First of all is a black box, which means you do not you treat the program as black box. You do not try to understand the program. You just feed different garbage to that program and see if it crashes. Then we have grammar-based fuzzing, generate new input, satisfying some constraints encoded by a grammar. Because you can imagine a black box fuzzing, if you just randomly generate input without any guideline. If there is a simple, let's say this is a web program. The web program take input from the network. For any input, it will calculate a CRC. Only if the CRC is correct, the program will move forward. If you just generate random input, you don't know this program will check that CRC. I mean, you are going to keep testing that CRC test all the time. The huge code after that, you will never have a chance to test, right? Then, so black box fuzzing cannot bypass that even a simple validation check. Then there is a white box fuzzing, which you fully know the program. You have the source code. That's one of the tools AFL does, is you have the source code. The AFL will build on top of a LLVM to instrument the program, generate test cases there, make things much faster and also more useful. So 4 generations of fuzzers so far. The first generation, early 2000, before that, is just some random input. So that time, fuzzing was not a very big thing. So fuzzing has been a very big thing in the last 15 years. Before that, early 2000, people think you are just feeding garbage to a program. What is the science behind that, right? Okay. Then after that, people realize, oh, there are a lot of things we can do here. Then second generation is protocol grammar, model-based fuzzing. The third generation, coverage-based fuzzing, using the program and try to cover more branches of the program. It knows the program, it says the source code, and it has a control flow graph, it has a call graph, and try to cover, then you can say there are more boxes there, the basic box. Try to cover more boxes. AFL, leap fuzzer, those are 2 examples fall into this category. Then right now, we are in the 3rd and 4th generation. So symbolic execution has been brought into fuzzing, had been closely combined with fuzzing, and we will see in a minute what is symbolic execution. Okay. So we can skip this one. So here is one example of coverage-based fuzzing. Let's say this is an example program. The bug is in 9.5. Only if you execute 9.5, you will trigger the bug. Okay. Other cases, you will not trigger the bug. But there are some very specific constraint if you can reach here. This is just one example, but it happens all the time in real-world programs. Only if your input follows the BOG, you will trigger the crash. So if you just randomly generate the input, so how likely you are going to trigger this bug? You need to do at least 256 times 256 to 556. So that will be how many? That will be 27,000, something like that. Test the cases before you trigger this bug, right? A little bit smaller than that, of course, before you trigger that bug. So the coverage-based fuzzing, they were try to understand the program. They will say, oh, there is a constraint, and this constraint is this. So next time I will just get the revert of this constraint and trigger a ladder pass. Then the next technique I'll talk about is called dynamic taint analysis. This was a pure software-based approach before, but recently we have seen some CPUs start supporting the taint feature on the CPU and memory. Okay, the idea of this approach is to monitor a program or code as it executes. It tracks the information flow through a program when it runs between some kind of source and between some kind of sink. So because this is runtime, at runtime the program will not run all the passes, right? So it will not be complete, but it will be very useful. It runs the program, observes which computations are affected by predefined taint sources. This has been very useful in 15 years ago, very useful to discover unknown vulnerabilities. This is a very expensive approach, not very efficient, but also it's quite effective. Fuzzing, you can imagine, it's very effective. Taint analysis, very expensive. You need to heavily change the program you are monitoring or change the system to monitor the program. I use one example to show you what does it mean by taint analysis. This is actually from a paper maybe published 10 years ago in Oakland, the hardest computer security conference to get in. Their acceptance rate usually is 12%. I've been working on security for, let's say, almost 20 years. I only have one paper there in 20 years. It's very hard, yeah. Let's say now we define a program, a very simple program. The program, so this is the BNF of this language. We define a language. In this language, we have a program. A program can have many statements. And a statement can either be an assignment, a store statement, a go-to statement, a cert, or a condition, if then else statement. That's a very simple language. Then the expressions can only be load or a binary operation with two expressions or a unary operation of one expression, or it can be a variable, or it can be get input from some kind of source, like user input, or from a sensor, from some other places, or it just can be a value. Okay. So that is a very simple language, and we're going to use this language to show how we can taint something. Okay, so we're going to use something called operational semantics. So how many of you, if you took compiler class or principal programming language class, you probably know what is operational semantics. So the BNF defines the syntax of the language, a programming language. If your syntax do not follow if your program do not follow the syntax, then your program cannot be compiled, right? So when you write a program, the compiler will check if your program follows this syntax. But this one, let's say variable equals expression. What is the meaning of this? This one is not defined anywhere, right? We didn't really define what is the meaning of this. Store this. What is the meaning of that? So to define the meaning of that, or the semantics of that, there are many different ways. And one way in PL is called operational semantics. The operational semantics has this format. It has a bar there. On top of the bar, it has the computation you want to do. Okay. Under the bar, it shows what is the starting state of the starting state, then what is the end state after this computation. So basically 2 states, okay, the start and the end. So basically it defines what the computation does. So you can say this can be defined at many different levels. You can define a single machine instruction, an add instruction. What does it do? You can define a say statement. What does it do, right? Then we use, let's say some simple example here. Let's say, which one is simple? Maybe a constant. Okay, a constant first. Here, a constant is a value, which is a v. Then the start condition is, the mu here is actually the memory map. Then the sigma is the code. Sigma is a code, mu is a memory. In this model, we didn't really model all the registers, okay? We only model memory, instructions. We do model PC and the next instruction here. So mu here means assume the current instruction set is mu, the memory is in this state. Then we have a constant v. Then the constant v is just constant v. It doesn't do anything, okay? But if we say there is define a variable, then the instruction, the code we have is mu here. The program, the memory we have is delta in this case. Then we define a variable. Then it means the variable is a location. The variable at that memory location, which is delta, should be updated to that variable, right? Then let's say a load. A load instruction where load, let's say this is a load instruction, where load to this is an expression for that load statement. The computation we have is we are going to evaluate that expression. That expression is a parameter of the load, okay? So that could be a very complicated expression. So we have to evaluate that. That evaluation end up with a number or whatever, we call it V1. Then what we're going to do is this is mu is memory. The memory location at V1 will be loaded into the variable V, right? So load is we load some variable, and this is the address we're going to load. Where basically load is reading from memory, right? So after this is what going to happen is when we load E, we will get V. So this syntax, this operational semantics defines what each instruction or each statement does. So when you read most programming language books, you do not say something like this, right? For any programming language you learn so far, you want to learn what does this statement do. They state that in plain text English. But because it's plain text English, it's not accurate sometimes, and it cannot be used for automatic reasoning. So if you dig deeper, most of the programming languages, they will have another book to describe its operational semantics using something like this. So this, kind of like in a mathematical way, clearly defined what is each operation. And because it's clearly defined, it can be used to automatically reason things. Okay. So how is this related to taint analysis? Let's say the taint analysis we want to do is we want to say if an attacker can do some damage to our system. The attacker will input to our system using get input. The get input will be, this is piece of program in code in our program, will be multiplied by 2 to assign to another variable x in this case. Then the whole thing, even though this is one line of code, the whole thing can be evaluated in a formal way like this. It can evaluate this. Then, if we change this, so here we need to define how do we want to taint things. Let's say, intuitively, you can understand this. Get input may get some malicious data. Then X is influenced by get input. So maybe we should taint X, means X is potentially malicious or potentially could be compromised, right? So that is something we want to define in the operational semantics. So in dynamic taint analysis, first we want to have a taint source. Then we have some kind of policies to define how this taint can propagate or flow among this program. For example, this one, if x gets its value from 2 times a taint value, then x should be taint as well, right? So this paper, they formally defined that how we can extend the previous operational semantics to more complicated operational semantics with different taint policies. So this is their contribution in this paper. Yeah, in the paper. Okay. So how is this really used? In 2010, there was a paper published in OSDI. That's one of the top operating system conference. It's called Taint Droid, information flow tracking system for real-time privacy monitoring of Android phones, actually. There was a longer version on a journal. So what this paper do is they use dynamic taint analysis to analyze Android applications and to say if those Android applications violate user privacy. So how do we define user privacy? Let's say this is back in 2010. Obviously, Android evolves a lot in the last 12 years. Let's say you install an app, and that app may ask you for some sensitive information. Like it will ask you for, can I read your contacts? Can I read access your pictures, right? But how do they really use those data? Do you know? Right? You don't, right? So they want to find out, after they access your contact information, are they sending it out? After they access your picture, is the app sending out your picture, right? So you can imagine how we can do this. So the pictures will be considered as tainted information. Then when the program runs, the picture, first of all, is a picture. Then the program will read that picture. Then it will become some data in the memory. It could be some variables, right? Then that variable will be considered as a taint one. Then that variable will be assigned to other variables, will be calculated, generating many different variables. And there are hundreds, thousands of variables when the program runs. So at the end, some variables, some buffer will be used to the send to network function. And that send to network function, that buffer, the data in that buffer, generated from your picture. If it is generated from your picture, it means they have been using your picture and sending it out. Maybe they encrypt it, maybe they cut it, but still, they are using part of your picture and sending it out. So that is a privacy violation. So that is how the taint analysis can be used. You taint the very first source, then monitor the program runs, and at the sink, at the end, to check if the data to be used at the sink, like sent out to the network, is also tainted. If it is tainted, it means there's a privacy violation, right? So a contribution of this paper is Android is a very complicated system. It has a modified Linux kernel. It has an Android Davik machine that time. It has its own virtual machine. So how to taint those things at different layers was a very challenging task. So you can imagine this is a very useful tool and also a lot of engineering work because you have to develop things at many different layers. Let's skip this part. Too much detail here. I want to show you something interesting here. So in that paper, they find out those applications. See, we still have those applications, like the Weather Channel, the movies, those applications. They analyzed those applications. They check what kind of permissions those applications ask for, like location, camera, audio, phones. Then this one is what number? Oh, yeah. So here is actually the findings. So they find out that they analyzed the 20 applications using the tool. They find out that they do violate users' behavior. They summarize those behaviors to like send phone information to the application provider server, device ID to them, or even locations to advertisement servers. They find out 2 applications, send out phone numbers, IMSI numbers, and also geo coordinates location to apps server. Okay, so this is confirmed with taint analysis. Also other things. Okay. I believe the last piece of technique I want to talk about is symbolic execution. So look at the name. You probably get a feeling what this is. You still execute the program, but all the program we're running so far, we can call them concrete execution. So all the variables, they have a concrete value. We execute them. So what if we do not have concrete values? Those variables, or some variables, only have a symbolic value. which means when we execute them, let's say there is a x plus 3 plus 2, and we do not really calculate 3 plus 2 is 5. We just remember we were calculating some number plus 2, right? Then later, when there is a predicate, there is a branch, then we can record, okay, at this branch, there are two branches we can take, and to execute this branch, those are, so a plus 2 has to be higher than 5. For this branch, a plus 2 should be lower than 5, for example, like that. So we feed those information back to the father. The father will know, oh, the next time I generate an input, at this branch, the input should have it should make sure it goes to the other branch. So that's basically symbolic execution. So in symbolic execution, some values, not all of them, because you can say every predicate will duplicate, will double the number of states or triple, right? So the number of states of a program will increase exponentially when you execute. When it's a concrete execution, you are executing only one pass of the program. But if it's a symbolic, you need to consider all the passes, then the number of passes increase exponentially. So you're not going to treat all the values as a symbolic value. So some values are concrete, some values are symbolic. So symbolic means they are expressions over some symbols. So when you execute a statement, execute an instruction, the output is not a concrete value. It's another expression over symbols. And you will only make them concrete at a later point when you feel that you need to do that. Let's say we use the same example here. X, we can treat X. Let's say we decide to treat X as a symbolic value. So we don't really care what the input the user gave, because that will be a concrete value. We don't care about the concrete value. We know X is a symbolic value. Then there is a predicate, x minus 5 equals 14. We go to a line, and x minus 5 doesn't equal to 14. We go to another line, right? Then what we do is here, the button. Only look at the button. When we execute the program, when we execute the first line X assignment, let's say the input is a symbolic, the symbol here. So our input is S. That's not a concrete value, that's a symbolic value. The X is assigned as 2 times S. So after that, we execute the next statement, X minus 5 this. So in concrete execution, you were actually X minus 5, right? But this is a symbolic execution. We will not do that. We will say, we will actually calculate 2 conditions for 2 different branches. One branch is 2 times S minus 5 should equal to 14. Another condition to go to the other branch is 2 minus 5 should not equal to 14. Then you keep executing at both branches. Keep accumulating more complicated conditions like this, right? So the purpose of this is, now if you want to trigger a particular pass in a program, you know exactly what the condition is over symbols. Then you calculate what my input should be to make that condition to meet, right? And that part is also can be automatically solved with something called a solver. Okay, so you feed the symbols like this into another tool like a set solver, and the set solver can tell you, hey, your S should be this particular value. to meet this condition, or it's not possible. Then you have a concrete value, then you fit that concrete value in the program again, then you can guarantee that part of code is tested, right? So that's why symbolic execution here is very useful. If you just randomly guess, we say the bug example before, if you just randomly guess, the chance you hit a particular path is very, very small, right? So symbolic execution has been widely used in research. There are many libraries we can use to symbolically execute different programs. This is still a very those are still very hot research areas. So that's basically all I have for this part. Any questions? This will not be in the exam anyway. Okay, if you find any of those very interesting, this class are still mainly talking about software security. Even this one, I'm mainly talking about software security. There are other interesting problems in system security. How do you modify the OS? We actually do a lot. We will probably do more software security, system security research than software research in our lab. So if you feel those things are interesting to you, you are very welcome to talk to me. Let's say if there any opportunity to work together on those kind of topics. It can be many different formats. If you want to work with me, I mean, you can do some independent work. Some of you need to do independent work. Or if you want to be a PhD student, you are very welcome to talk with me. Or if you just want to do, some of you do master thesis in the future. If you want to do master thesis on those topics, also not necessarily software security. I'm also doing other security projects. I actually like to hack passwords. I used to hack picture password, text-based passwords. We develop system to hack those things. And we also do design all kinds of authentication systems. For example, 2 weeks ago, I went to CCS. I presented a paper. So we worked on how to, on your commodity phones, how do you authenticate using just a camera and also the microphone. So many phones, they have face recognition. So that recognition is basically authentication, right? But face recognition system, there are a lot of issues. You can fool the system with a picture. Of course, now there is a liveness detection to make sure that's not a picture. But not every phone has that hardware or algorithm, right? Then also there is privacy issues. Many people worry that the software should not use my face to authenticate. Also should not use my fingerprint to authenticate. Privacy issues. That's why there's a new authentication method called hand authentication. Amazon has been using that in some of the Amazon supermarkets. What is the Amazon supermarkets? What are they called? Amazon have some physical supermarkets, right? Yeah. They also have Whole Food, but I don't know if Whole Food has this. So what you do is you can use your hand to authenticate you are you. Some phones are also doing that right now. But obviously, because most people do not worry about the privacy of hand, right? But hand also has a lot of personal traits, rich characteristics can be used for authentication. But still, it's not that reliable. So what we propose is, on your phone, you just do this to unlock your phone, authenticate your hand, but that's not secure enough. What we also do is, when see, what do? One hand, you are going to use the phone to look at it. Another hand, you are holding the phone. So the holding hand, what we do is, from the microphone, we are going to send out inaudible sound. And that sound will be reflected by your hand and pick up by the we send out a sound from the speaker, inaudible, reflected by your hand, then we pick it up at the microphone. Then from that captured signal, we come up with a lot of features, and we try to authenticate users using that. So it's kind of like in mobile sensing, and we prove that it's quite reliable if you carefully design the signal. So we also do research like that. We also do research in actually user study, like usable security. I was part of a team that we just want to know. So how many of you get spam, telephone spams right now, every day, right? So it's not that serious anymore. 5 years, 6 years ago, it was really bad. I get a lot of telephone spams every day. So there was one day I was wake up by a fake chase call, like 6 in the morning. A fake chase called me, and my credit card is stolen, blah, blah, blah. So I was not happy about that. So I went to my lab, told my student, this problem is getting really serious. Okay, but why we cannot stop that? So we first studied how they actually conduct those kind of telephone spam. That ended up with a paper in the Oakland. That's the only paper in the Oakland. So sometimes the IEEE security and privacy, the hardest one to get in. Then we design a new approach to authenticate the caller IDs. So one of the problem is that time, back 5 years ago. So now all your phones have some kind of defense, right? It tells you, my Android tells me this is probably a spam. But 5 years ago, no such things. Then there could be the caller, so you get a phone number, who is calling you? That phone number could be spoofed. That's not a real phone number, right? So we propose a new approach, how do we authenticate that phone number? And also we want to know, do users really fall into this kind of scams, right? So what we did is, that's when I was back in Arizona State. So we spammed 3,000 employees at Arizona State. We create a fake, we studied how those spam work. We create something, then we called 3,000 employees at Arizona State University automatically to say where they fall into this kind of scam. Ask them to input their social security numbers. And a lot of them did fall into the scam. So that also was an interesting research we did. So you can say, sometimes those research are not those hardcore technical, but still very valuable to the community. Okay, so anyway, so if you want to do research in security, let me know. So, okay, that's all basically for today. You still have homework to do today and also next week. But we will have our final CTF, I think it's December 14th. I will give out more detailed information next week. Next week, it will be simple. We just watch a video together. But I still expect to see you, and I can answer some questions. Okay, cool. See you guys next week.